Our speaker today is Georgii Riabov with the talk Strong Flow Modifications of Stochastic Flows. This is a joint talk with Olivier Raymond. And as far as I remember, Raymond was the last foreign visitor at our department before the first lockdown due to coronavirus. Was it just statistical thing or not? I don't know. Okay, let's start.
Okay, thank you for the introduction. The topic of my talk is strong flow modifications of stochastic flows. I will start from the definition of the main object that I consider. So I will work in a locally compact separable metric space. By F, I denote the space of measurable mappings on M, by now, a standard definition of a stochastic flow is a family of random elements in F that satisfy a weak evolutionary property, act independently on disjoint intervals. They have stationary distributions in the sense that the distribution of the mapping psi st as a random mapping depends only on t minus s. And also we have two assumptions on continuity. It's a kind of continuity in probability. We have a continuity in time and continuity in space variable x. So here, weak evolutionary property essentially means that the composition of two mappings from the flow at point x almost surely equals psi rt of x, and the exceptional set in general can depend on all arguments r, st, and x. So yes.
Excuse me, can you just the last one condition? F is what? F is going to 0 on infinity or have compact support?
This is the space of continuous functions that vanish at infinity. So it does not necessarily have a compact support.
It vanishes on infinity. Is it necessary to put the square?
No, it can be. It can be convergence in probability, for example.
Yes, but a square of such function is also the same such function.
Yes.
So it is enough maybe to have that all such expectations.
Yes.
Okay.
Essentially, it is a convergence in the probability of f from psi. So these last two assumptions they are related with the failure property of finite point motions. So we define finite point motions as the probability that the flow sends points x1, xn into a set B during time t. And the last two properties from the definition, they imply that P and T is a failure transition function on m to the power n. Of course, they are consistent in the following sense. So the n-point motion defines k-point motions when k is less than n. And we have so-called coalescing properties. So if we take the same points, we will always live on the diagonal of the space. And the relation between such failure transition functions and stochastic flows, they are stated in the theorem by Lejean and Raymond, which says that to any such Pn, there corresponds some stochastic flow with such finite point motions. Okay. My aim is to improve this result in some cases. We will say that a stochastic flow is strong if the evolutionary property holds with probability 1 without exceptions. and it is an open problem. So if any stochastic flow has a strong flow modification.
Excuse me again. This psi st is continuous random mapping, or we don't have any assumption about its regularity?
Here, in the definition, psi is a random element in F, and F is a space of measurable mappings.
Okay, space of measurable mappings with a cylindrical sigma field.
Yes, it is not a good space, and
yes,
there is a well-known theory by Arnold and Shoitsu. When we have a weak flow in a good space of mappings, it can be automatically made a strong flow. But this space of mappings must be something like a Polish group.
But my question is the following: if we don't assume that psi st is a random element in good space, why we can say that superposition is equal to another one, and that is a probability event?
I don't say that it is. I don't say that it is a probability event. It means that outside a set of probability 0,
we have equality.
We have equality, yes.
Okay.
But in fact, okay, the flows that I will construct, for them, this will be an event. Besides strong flow, I also will try to achieve some measurability properties. In particular, I want this flow to be measurable in S, T, X jointly, which also is not in the main construction of Legendre-Raymonde. So see, the first question is open. I will formulate some additional assumptions on transition functions under which, again, in some cases, we can achieve strong flow modification. And one of these assumptions I will formulate right away. This is assumption number 3 is a well-known condition under which trajectories are continuous. The interest to such questions appeared some time ago when we started random dynamics.
What is K? K is capital.
Here, K is any compact, and R is
for any compact. We have this uniformly.
Yes, it is not the weakest one. Actually, you can remove supremum and assume it only for each x, but for me, it will be important that there is supremum here. So the interest to such questions arose when we studied random dynamical systems that generate stochastic flows, in the sense that the stochastic flow psi st of x can be represented as a transformation of this type, where theta is a measure preserving transformation of the probability space, but t minus s, okay? And the existence of such random dynamical systems allows to study symptotic behavior of stochastic flows and so on. And also today we will see that the question about strong flow modifications is closely related to the so-called bifurcation points, which I will define later, and it is also an object of interest. Actually, bifurcation points are points where the flow property can fail. Okay, let me introduce some notations to present the results. So first of all, we can assume that the metric is complete and all bounded sets are relatively compact. So C is a space of continuous functions from some interval into M. X is a space of all continuous functions from any half line S infinity to M. The set X is equipped with the natural distance when we have two functions. They are close if their initial times when they start, if they close, and if they are uniformly close on large enough segment. So the metric in X, it is a metric of uniform convergence on segments and the convergence of initial times. We have proved a lemma that for any Polish space, there exists a measurable mapping L, which sends a sequence in X into element in X in such a way that a relatively compact sequence always is sent to its limit point. So I will fix such mapping in the future. And for any sequence of continuous functions, Sn will be denoted by Sn. I will denote the initial time and Xn the starting point. Also, Is is a function that started before time S. Okay, I will construct stochastic flows using the notion of the skeleton. So a sequence of continuous functions from X will be called a skeleton if the first property is coalescing. It means that when two functions meet, they then equal after this meeting time. Also, the set of starting times and starting points is dense. And the third property says that if we take a compact L in the product and consider all functions from our sequence that were in this compact, and consider their restrictions after this time when they are in the compact, then all this set of functions must be also relatively compact. So the function may hit L, or it may start from L, and all this set of functions must be relatively compact. By Sm, I will denote the space of all skeletons on M. And in fact, one can show that, so Sm is a subset of x to the power n. Here we have a Borel sigma field, and in fact, Sm is a Borel set in this space of sequences of functions. Okay. The first result is that there exists a measurable mapping theta. Its arguments are the time, the point in space, and some skeleton. And the result is a function, a continuous function. So this mapping is measurable, and it has the following properties. So every continuous function for all s and x, it is a continuous function that starts at s from the point x. So, and the second property is that theta actually preserves trajectories from the skeleton. So if we apply theta to a point sx when x is the value of some trajectory, then as a result we will get this trajectory after time s. And the construction is the following. Let us fix some sequence of measurable functions on M. They take positive values, and point-wise they decrease to 0. By nk sx, I will denote the first index n such that in the epsilon neighborhood of x, there was some trajectory of the skeleton. So this is phi n, this is x, and this is the epsilon k neighborhood. And by phi k, I will denote the this trajectory after time s. Okay, so in this way we can we get some sequence of continuous functions, and let us apply this mapping L that chooses its limit point. In fact, from our assumption on the skeleton, the sequence is relatively compact, because at time s it lives in a relatively compact set. So as a result, we will get some limit point of this sequence, and this limit point will start at time s from point x. Now, the point is that if x is if x is a point on the skeleton, then this sequence is stationary. Hence, we get its limit, and its limit will be a trajectory from the skeleton at some point, let's say n star, but at these functions phi n and phi n star, they are equal at s, so the restrictions after s also will be equal. Okay, so we have such a mapping, and now the idea is to take to sample a skeleton from the weak flow and apply this mapping theta to this skeleton. So by psi 0, I will denote a stochastic flow, some dense sequence of starting times, and phi capital N will be trajectories of this flow that started from points Sn, Xn. We can look at phi as a random element in X, a random sequence in X, and the most strong assumption is that with probability 1, this sequence is a skeleton. One can check that from the definition of the skeleton, there were 3 points. So first 2 are satisfied. Essentially, this assumption 4 means that when we take trajectories of the flow that live in some relatively compact set, then this sequence will be also relatively compact. It is an open question whether this assumption independent from previous ones. Okay, now in the construction of this mapping theta, there was a sequence of measurable functions epsilon k, and I will construct it using the failure property of finite point motions. So it is well known that this function is upper semi-continuous in x and y, and epsilon k of x will be defined as the following infimum, well, minimum 2 to the power minus k. Okay. And the idea is that if y is in the epsilon k neighborhood of x, then the distance between corresponding trajectories from the flow will be small with high probability. And this sequence is non-increasing. It converges to 0 pointwise. And in fact, these functions are measurable exactly because of upper semi-continuity of GK. Yeah, so GK is upper semi-continuous. This function GRK is also upper semi-continuous. And from this, we can easily prove measurability of epsilon k. Okay, so now we construct the flow theta by applying this function big theta to our random skeleton phi. And in this way, indeed we get a modification of initial flow psi 0. Moreover, this modification is measurable in all arguments, and moreover, it preserves trajectories of the skeleton almost surely. This measurability and this property, essentially, it follows from our construction of function big theta, and the fact that theta is a modification of psi 0, it follows from our choice of epsilon k. So indeed, at time s, the skeleton, yes, the approximating sequence was chosen in such a way that distance to x is less than epsilon k. So we get this inequality, and it means that almost surely phi k has a limit. Since our mapping chooses a limiting point, it will choose, almost surely, it will choose psi 0. This flow theta has one more property. It almost surely satisfies evolutionary property at some random times. These random times are stopping times for the natural filtration of theta. So the lemma says that almost surely when a stopping time sigma is finite, we will have the evolutionary property. Essentially, the proof repeats arguments from previous slide, but we apply them to the point xi, which is the value of theta at time sigma, well, at point xi at time sigma, we also define these approximating indices, and all these things, they are a sigma measurable. So basically, we can apply the strong Markov property at time sigma, and similar considerations show that this probability is less or equal to 2 to the power minus k. So this just follows from the strong flow, strong Markov property of two-point motions. Okay, in some cases, the flow theta is actually a strong flow. One such case is that when after time t, yes, if with probability 1 for any times s less than t and for any point x, our trajectory of the flow theta simply coincides with some trajectory from the skeleton. This is a consequence of the fact that theta preserves trajectories of the skeleton. So we get a strong flow. And a sufficient condition when lemma 4 can be applied is when a sequence phi is instantaneously coalescing in the following sense. When we fix two moments of time s and t and look at the values of this sequence of functions at time t, a function that started before time s. So this set is locally finite in the sense that in every compact we have only finite number of values of these functions. So if almost surely the skeleton possesses the instantaneous coalescing property, then theta is a strong flow. In fact, in this case, since we have this locally finite property, then in neighborhood of every point y, here y is theta st of x. In the neighborhood of every point y, we have only finite number of values of the skeleton. But on the other hand, at these values at time t, they converge to y, because this trajectory is the limit point of some approximating sequence of functions from the skeleton. It means that from some moment they just coincide with y, so the restriction of theta after time t is phi n of u, is some trajectory from the skeleton. But on the other hand, since theta preserves the trajectory of the skeleton, we have this equality, and this is y. Okay, so in this case, we get a strong flow. A sufficient condition for the instantaneous coalescing property is also known from the paper Evans, Morris, and Sen, which I already talked about some time ago. So the condition is that it is slightly modified. So for any compact K, we have some family of positive constants. Alpha kappa must be bigger than 1. Okay, and when we have two trajectories that started at distance epsilon, then with a bounded probability, they do not meet, this is tau, and they do not leave a compact, this is sigma, during the time which is proportional to epsilon to the power alpha. So this is the first assumption. And the second is, it's a more geometric assumption. If we have a set A with more than n points, then from this set we can find two points at distance proportional to n, 1 over n to the power kappa. Now, for a compact set K and for moments s less than t, by AK, I will denote values of the skeleton that are in the set K at time t, but also they have been in the compact during time from S to T. And essentially, the result of Evans, Morris, and Sen is that almost surely for all t greater than s, this set will be finite. The set of values at time t will be finite. If the space M is compact, then it immediately implies the instantaneous coalescing property. If M is locally compact but not compact, then we need some additional assumption. We assume that there is an increasing sequence of compact sets KL that cover M. Okay, and they have the following property. For every compact from this sequence, K indexed by K, we can find a bigger compact K indexed by L, such that if phi n of t was in smaller compact at time t, then it was in a bigger compact, but during some fixed time from R to T. And under this assumption, it is easy to show that when we have conditions 1, 2, and the assumption is satisfied, then we will have the instantaneous coalescing property of the skeleton. Okay. This condition is easy to check on metric graphs. So a metric graph is just a space where we have a countable set of vertices and a countable set of edges between vertices. and these edges are isometric to intervals. They can be infinite. Okay, like this. And so I assume that the degree of every vertex is finite and bigger than 0. Okay, it cannot be 0. Okay, so for metric graphs, this geometric condition of Evans, Morris, and Sen is satisfied with kappa equal to 1. So if we prove an estimate of this type, where here we have square, then we can say that our skeleton satisfies the instantaneous coalescing property. And actually, it is enough to prove this inequality only for simple compacts. By simple compact, I understand the following set. So it has one vertex, and it has some segments on the neighboring edges of this vertex. So this is a simple compact. If it has no vertices, we can just take a point on the edge and also add two segments. So this is a simple compact. Okay. And on the previous talk, I announced a result which now is proved, and it's about coalescing independent Walsh-Brownian motions. So a Walsh-Brownian motion is a process of the following kind. So we have a metric graph. So on each edge, this process behaves like a Brownian motion, and when it reaches the vertex, it chooses which edge to go in some sense. And the probabilities are defined. So for each vertex, we associate a family of these probabilities. And this process can be defined through the generator as follows. Okay, now by Pn, I will denote transition functions that correspond to independent Walsh-Brownian motions on the metric graph that coalesce at the meeting time. So it's like a generalization of Aratia flow, but for metric graphs. Yes, something like this. And it turns out that the corresponding flow exists. So since the estimate of the inequality of Evans, Morris, and Sen must be proved only for simple compacts, and since we add the condition that processes don't meet and don't leave a simple compact, we can reduce considerations to the case when M is a star graph. So then this is the usual Walsh-Brownian motions. So M has this form, and it is enough to prove that actually in infimum over all points in this M of probabilities that independent Walsh-Brownian motions will meet before time proportional to distance squared, this infimum is bigger than 0. Okay, to prove this inequality, I will consider several cases. First case, when one of these processes starts from 0. So now 0 is the only vertex. In this case, the needed probability, the needed estimate on the probability follows from scaling invariance. It is known that if we divide x by lambda and multiply time by lambda squared, we get again a Walsh-Brownian motion with a different starting point. So here, if we divide by x squared, okay, we multiply the time by x squared and divide by x, so we get a probability that two independent Walsh-Brownian motions meet before fixed time beta. One started from 0 and the other started at distance 1 from 0. Now, of course, there is one pi which is bigger than 0, and with positive probability at some moment of time, both processes x and y will be on the same edge, and then with it is easy that during the remaining time, two independent Brownian motions will meet and before leaving this edge. Okay, so for each j, this probability is positive, and we have only finite number of edges. Next case, when processes start from different edges, then we get the needed inequality with a factor 2. Now the distance from x to y actually equals to the sum of their absolute values, and by tau y I will denote the time when y is at 0, and so this probability is estimated as follows. So first we wait until y gets to 0 and consider the event that y is at 0 before time y squared. At this time, x is a distance of this form, yes, x plus y from 0, and the time to meeting is less than x plus y squared. So this is, of course, an estimate from below. And now we use the strong Markov property at time tau y. And this probability, actually, it was estimated before, because now x plus y squared is bigger than this x tau y. So it can be estimated using the previous lemma by SP of 1. And what remains is the probability that the process y was at 0 before time y squared, and x at this time was a distance x plus y from 0. Now we know that absolute value of x in distribution is the same as reflected Brownian motion that started from x, and hence we can estimate the probability of this event by the probability for the Brownian motion. And this probability I denoted by phi. So in the end, we get an estimate of this type. So this is P of 1. And here we have expectation of indicator that tau y is less than y squared, and times this function phi. Okay, but y, again, y is scaling invariant, so we can divide by y squared and get this expression, which is bigger than 0. And essentially, similar considerations work when processes start from the same edge. Here, by Q, I will denote the probability that two independent Brownian motions started at distance 1 and they meet before time 1. Okay, and choose epsilon in such a way. And now the estimation will be actually similar. So we also can scale everything, yes, by factor r, and get the probability that so one Brownian motion was started from 1, another started from r, which is bigger than 1, and they meet before time r minus 1 squared. If we add, yes, so this is greater or equal. If we add the condition that the second process didn't leave the edge, we can rewrite everything in terms of independent Brownian motions, and hence we can get the following estimation. Now, this probability, again by scaling invariance, is Q, and this probability by reflection principle can be written as follows, as the probability for absolute value of Brownian motion. Now, if r minus 1 is less than epsilon, then by our choice of epsilon, this probability is less than q over 2, and we get a positive lower bound. And if r is bigger than epsilon, 1 plus epsilon, then essentially we have the same consideration. So we wait until a process y gets to 0, and also simultaneously x is not far from 0, and everything then works. So I will not stop at this. So we see that we have a strong flow of coalescing independent Walsh-Brownian motions. So what if we don't have instantaneous coalescing property? In this case, theta may not be a strong flow, and another modification may be needed to get the strong flow. To define this modification, I will discuss so-called exceptional points or bifurcation points. So phi n is a skeleton. By kst epsilon x, I will denote the closure of all trajectories phi n during time from s to t, and these trajectories were in the epsilon neighborhood of x. Okay, and by k without epsilon, I will denote the intersection of all these sets. So it is a non-empty compact subset again. So here works our assumption on the skeleton, and by nu I denote the family, the number of points in K, which can be infinite. Tau is the first moment when nu is greater or equal to 2. So we can approximate, for example, point X at time S, like this, and in the intersection, all functions that are in this set, they can be equal during some time, but then we can get bifurcation. Okay, we will say that the point Sx is exceptional if we get this immediately. So when tau Sx is equal to S. And the consequence of this definition is that if that before time tau Sx, we don't have bifurcations, so this set contains only one function, and this function is the trajectory of our flow. if tau is finite, then the trajectory of the flow at time tau it exactly hits this exceptional set. Now, it turns out that if y is the value theta st of x, then before the bifurcation time of y, we have the strong flow property. This shows that if E is empty, then theta is a strong flow. Then theta is a strong flow. The idea of modification is to change the trajectories of the flow theta when they hit E. But the set E is random, and it can be complicated. It can have complicated structures. So I will define a closed shell of E as a closed subset that almost surely contains E. That almost surely contains E. Now, sigma Sx is the time when theta hits this closed shell of E, and I define psi as a, so before hitting time it is theta, and after hitting time, psi is the value of theta from this point. So in some sense, we okay, so in some sense, at time sigma, I make this evolutionary property by definition. Then psi is a measurable modification of theta. It also preserves trajectories of the skeleton, and this exactly follows from the fact that sigmas are stopping times. Yes, and we know that at stopping times theta almost surely has the strong flow property. Okay, and the theorem is the following. So assume that if t is bigger than sigma, and if at time t psi is in this set F, then after time t psi coincides with the skeleton. Then psi is a strong flow. Actually, in the proof, I will consider a few cases. So S is less than T, X in M, and by Y I denote psi st of X. And what must be shown that after time T, psi Su of X equals psi Tu of Y. Okay, if T is smaller than the heating time of F, in this case, Ty is not in F, and we know that up to this time, we will have strong flow property. In particular, we will have it up to time sigma. Okay, but at time sigma, simultaneously, both the trajectories will be redefined identically. So we will have strong flow property also after time sigma. Second case, when T is equal to sigma S of X. In this case, Y is actually the value of theta at time sigma, and we have the flow property by definition of psi. Similar thing holds when S less than sigma, sigma is equal to T, and T is less than sigma Y. So before heating F, we have a strong flow property, and then we have it by our definition. No. At the time of heating F, so the assumption of the theorem works. So after this time, we coincide with the skeleton, and this implies the strong flow property. Okay. Finally, if T is bigger than sigma, if at time T where Y belongs to F, again, the assumption of the theorem works. And the last case, if sigma is less than T, but we are not in the set F, then again, we can, before heating F, we are in, so we have the flow property, and after heating F, the assumption of the theorem works. So this is some kind of relaxation of our condition. If assume two properties. So if S less than sigma, then at time sigma, the flow hits the skeleton. And if S is equal to sigma, then immediately after this time, okay, for any T bigger than S, the flow coincides with the skeleton. And it is not hard to check that these two properties imply the assumption of the theorem. As an example of this type of flows, we can consider the flow of solutions to Tanaka SD. It is known that this SD doesn't have a unique strong solution. So we will define finite point motions of the flow as follows. So x1, xn is a solution of the following problem. They are solutions to Tanaka SD, and when they meet, they coalesce. Okay, and then there is a unique weak solution of this problem, and the corresponding distributions I will denote by Pn. Okay, so now let us consider the skeleton. For each trajectory from the skeleton, I will denote this stochastic integral. In fact, this is B. And as a consequence, the increments of Wn and Wm are equal, okay, when both are defined. And by sigma n is the time when phi n hits 0. So it is, first of all, we have this relative compactness property. So if we look at all the trajectories that were at time S in a compact L, then the set of these trajectories is relatively compact. It follows from the representation for solution of Tanaka SD. So we know what is absolute value of phi n. And since increments of Wn and Wm coincide, we can choose one trajectory for all for all n. So the modulus of continuity of absolute value of phi n is estimated by modulus of continuity of one trajectory Wn. Well, since phi n is continuous, we can also get modulus of continuity for phi n. Okay, so relative compactness. We have relative compactness. Also, the closed shell of set of exceptional points is just r times 0. So this is all our exceptional points that they are here. Indeed, if we start from x, which is bigger than 0, then here all increments are the same, and we can get only one trajectory in the limit. This is it. So one more auxiliary result is that almost surely the set of moments when skeleton hits 0 is dense on the real line. And it is enough to check the conditions of our theorem for Tanaka flow. So there exists a strong flow modification of a Tanaka flow. Now I check these relaxed conditions. So if sigma is bigger than s, sigma is the time when theta hits 0. Theta is a limit of some approximating sequence. And in fact, if we choose a trajectory from the skeleton that is less than absolute value of theta, then we know the expression for absolute value of phi n in terms of theta. And from this expression, we see that at time sigma, this trajectory from the skeleton will hit also 0 and will coincide with theta. The second case is checked similarly, but now we start from 0. Now we start from 0. St, we start from 0. And we know that somewhere here we have a trajectory from the skeleton. And we know that since S and sigma are equal, somewhere here we will also have 0 of theta. Then when we consider the approximating sequence, it will follow that at time sigma, all this approximating sequence is at 0. So after this time, actually, our trajectory coincides with the skeleton. Okay, so these are results that they wanted to show today. One comment is that a relaxed condition of the theorem 3, it is not applicable to the well-known Georgii flow. So our future research will be about verification of the condition of theorem 3 for the Georgii flow. Thank you for your attention.
Okay, thank you very much. Maybe somebody have comments or questions, please. I have a question. Can you non-formally characterize this exceptional set of points? Can we say that some change of probability law of motion happens in these points, or what is the nature of this exceptional set?
Well, by this set of exceptional points is where we have. I think it. From the point of view of stochastic differential equations, it is the set where we don't have a unique strong solution to this equation. If we can put it like this. For example, for Tanaka SD, of course, before we hit 0, we have a unique x. Yes, and 0 is the only point where uniqueness fails.
Can we say that if we have a regular graph and actually, as you consider it, with these all Poynting motions, then we can characterize all points when we consider weak flow or possible points like in Aratia net, like 1, 2, or 2, 2 points, and so on. Can we do the same in this case?
It is very interesting. I hope to do it sometime. Of course, it is very interesting what happens at the vertices. So maybe we will not even get a flow of maps. Maybe we can get some flow of kernels. So as for Aratia flow, we have a Howitt-Warren flows. Maybe something can be made also for Walsh-Brownian motions.
Okay. And also, this is my last question. I remember maybe one of the initial works of Darwin, construction of non-homeomorphic stochastic flows. And the problem was related to the general phase state. Today, you consider it only locally compact spaces, and moreover, examples are related actually to the graphs. What do you think? Maybe using some triangulation procedure and your construction, one can, by approximation, get the flow with good properties on a more complicated space, for example, on all plane or something.
Maybe.
It seems that such regularization property and such a skeleton can be used not only for the for the graph. Then we can use another limit procedure.
Yes.
Okay.
At least the flow theta, it is not necessarily defined. And so M was not important that it is locally compact space. So we always can get measurable modifications, but they will be weak flows.
Okay, interesting. Okay, thank you very much again. And maybe you can announce next speaker.
Yes, it will be Yannick Steinbeck.
Okay, interesting. He also is working with the stochastic flows, I think. Okay, so for today we finish our job. Thank everybody and see you next week. Bye.
Bye.